Thanks for having me. My name is Manuel. I'm a PhD student in Germany, and as mentioned already, today I want to talk a bit about this algorithm that we have. It's surrogate-assisted multi-objective optimization for problems with nonlinear constraints. And 2 years back, I already gave a talk on a similar topic. You can find it on YouTube. And basically, this is a short follow-up. And I can give you the short and sweet before. It's basically screw the old code, but keep the theory. And we'll start by looking at a bit of that theory, gloss over some details, and see what we've done so far. So the old package, it was meant to find critical points for multi-objective optimization problems that looked like this with k nonlinear objectives. And then we were also able back then to incorporate convex constraints like these linear constraints here. And what we did back then and what we do still is use these local nonlinear surrogate models for the objective functions. And we do that in a trust region algorithm. And then we don't need derivatives because we have these trust regions in which we have the models. And well, I'm a bit unhappy about how that package turned out. It grew according to the needs of the project that I worked on, and it was a bit messy in the end, and there was still much left to explore, but it never got registered or anything. One of the things that we always wanted to do were these nonlinear constraints instead of like linear convex constraints, which led to the new successor package, Compromised JL. And if you don't know anything about multi-objective optimization, generally it's about finding trade-offs between the different objectives, and then you usually get multiple solutions, which we call the Pareto set or Pareto front, and you can see it on the right in blue. And there's also some necessary condition, which basically means the gradients vanish. It's a bit hand-wavy. You can look into the presentation 2 years back or our current preprint for details. I'll just show some pictures of what we do conceptually. So instead of taking the steepest descent direction, you can use the multi-objective steepest descent direction, which basically is a projection onto the convex set of negative gradients. Now we don't want to take the true derivatives. We use our surrogates and then get an inexact steepest descent direction. And we then have to find some step size by minimizing our objectives along that direction. And because we don't trust our surrogate models too much, we do that within a trust region. And then if our trust region looks nice, is convex, we can project back onto that trust region and minimize along that projected direction in our trust region. And if our constraints are nice, we can just intersect them, project onto that nice set, and handle these easy constraints with that projection approach without too much hassle. But if our feasible set doesn't look so nice, if we have general nonlinear constraints, then we employ our favorite trick. We just linearize by taking the derivatives. And now we're having the same problem as before. We might not have the true constraint derivatives. So our idea was to basically use the same kinds of models for these constraints. And then we use that set within a trust region to find the next iteration site. And if you look closely, this next iteration site must not be, or it could happen that it is not feasible for the true feasible set. And that's why we need a few more tricks like this filter, which is imported from the single objective optimization literature and which guides our iterates towards the true feasible set asymptotically. We must make sure that our surrogate models conform to certain error bounds, and we know how to construct these kinds of models. And then we can also use them to maybe guess where our feasible set is. And now coming to the code and a bit of the history of our code. Well, we had this package Morbid, which I didn't quite like. And then we had to present some code for the preprint, and what we did basically was copy-paste the most important snippets of code in a Pluto notebook, which was more lightweight and sleek, but in quotation marks, because it still took ages to do all these plots that we did. And what we did was basically just look, does this work? Basically for small experiments. Here we had two parabolas. The critical set is shown black, and we just wanted to see, can we avoid the non-feasible part in red? And indeed we could. And well, the blue line shows that our radial basis functions again worked very well in this kind of setting. We also tested non-convex problems and saw that we could find critical points. But now the reviewers requested more experiments, so we had to actually improve the code. And that's what we're doing currently in the new package. It has a nicer name, a very nice acronym, I guess, Constrained Multi-Objective Problem Optimizer with model information to save evaluations. And we want to make better use of what Julia offers. What does Julia offer? Well, in particular, JUMP and all the solvers it offers are very well suited to the step computation problems that you saw earlier, and it makes it easy and fast to tinker with different descent methods. Then multiple dispatch is just very well suited for this surrogate modeling stuff, and all these autodiff packages also make it very convenient for us to just do some testing in development. And our interfaces internally are designed so that if the need arises, we can hopefully easily interface with either JUMP or some SciML optimization package. Here's some snippet of code that at least didn't error yesterday. So to just show what features are available right now, so we can set our objectives out of place and in place if you want. We have an autodiff backend built in, and we can specify what the surrogates to use. And then it does what you saw on the plots, and we now want to do some testing to make sure it really does what we hope it does. What I'm working on is also some graph structure to use surrogate models for certain subcomponents of functions. And I'm also hoping to improve the convergence speed with some nonlinear CG stuff. That's basically where we're at. You can look at the code. It's not registered. I hope to register it in September, I guess. And thanks for listening.